Great. So today we have, welcome everybody, sorry. It's a pleasure to having you today. We have our second webinar for this new series of webinar expanding our knowledge about the study of global change, organized by the regional representative of Central and South America of patients. This new webinar series aims to provide different perspectives from various disciplines, creating a space for exchanging new ideas and approach about how to study and addressing the global change. So, Christian, go ahead and introduce our new speaker, Shivangi Tiwari. She is a PhD candidate and she will discuss about remote impact of the mid-Holocene Saharan vegetation on South American hydroclimate.
Thanks, Karina, and welcome everyone. So yes, we have Shivangi today. Just a little bit about her presentation. About her as well. She's a PhD candidate at the University of Quebec in Montreal. Before this, she studied geology and paleoclimatology at the Indian Institute of Technology, Turkey, and the Indian Institute of Technology, Kanpur. Her previous research focused on proxy reconstructions, but now she studies past climates through the lens of paleoclimate modeling. Thank you, Shivangi, for joining us today. Congratulations on your achievements. Please note that Shivangi will deliver the presentation in 30 minutes, or it lasts 30 minutes, and at the end we will address the questions that anyone could have. You can raise the hand, and then we can also have questions in English or in Spanish. But without further ado, we invite Shivangi to begin her presentation.
Thanks, Christian. Thanks for giving me a platform to present some of my research. This is part of my PhD research at, as you mentioned, I'm at UQAM, it's the University of Quebec at Montreal. And I'm just finishing up my PhD. And for my PhD, I primarily looked at the mid-Holocene Green Sahara. I'm going to be a bit free with the terms because I think a lot of us are paleo people over here. So I'm going to be talking about the remote impacts of the mid-Holocene Green Sahara. And if you're wondering why an Indian in Canada studying African climate is at a South American platform, I promise I am going to link these things together. So yeah, let me go ahead. This work has been carried out in collaboration with a lot of people.
Sorry, Shivangi.
I have not shared my screen yet.
Yeah, exactly.
Right. Okay, it should work.
Yeah, that's perfect.
Okay, awesome. I'm just gonna hide. Okay, should look better. Okay, so a lot of this work, yes, it's been carried out in collaboration with a lot of different people in Canada and the US, as well as people in Brazil. It's really a multi-model approach. It involved people at different modeling centers. So some of the simulations were carried out at the University of Toronto, some of them at NASA GIS, and some of them at Connecticut. So yeah, so I should thank this large team which made this possible for a beginning PhD student to approach a multi-model comparison. And today I've structured my presentation to first talk about the mid-Holocene Green Sahara, to sort of give a background of why it's even relevant to someone sitting in South America, and then how we designed our study, then some results, next questions, and then just trying to put these results into a broader picture. So Yes. Okay, I want to begin by discussing the West African monsoon because it's kind of central to whatever I talk about. The West African monsoon and in general, the climate overall of Northern Africa, it's primarily governed by the seasonal migration of the intertropical convergence zone. And so during boreal summer, you see some precipitation reaching till just the southern limit of the Sahara. So that's the region which we call the Sahel. And in boreal winter, it goes further south, but that's not what we're looking at. And this seasonal migration of the ITCZ is primarily governed by insolation. So in the paleoclimatic history, whenever insolation changed, we could expect that not just the African monsoon, but really all monsoons would also undergo some changes. So this is the present day Northern Africa, and this is an image which in colors it shows the different vegetational bands, and then the different contours they show the isohyates for the mean annual precipitation. And you see that all of this white here, it's the Saharan region of the present day, which gets less than 100 millimeter per year of rainfall today. And then going from north to south, we're going to leave out the pink patch. It's mostly the Mediterranean influence, so that's not directly related to the West African monsoon precipitation. But going from north to south towards the equator, you see these different vegetational bands which crop up because of different zonal precipitation amounts. So if you have the grasslands, you have the wooded grasslands, you have more complex vegetation and more woody vegetation. In the equatorial regions, you have the forest cover. So this is the present day picture. And if I were to compare this with the Holocene, primarily the early and middle Holocene, so roughly say from 11,000 to 5,000 years before present, you see that the isohyates have moved up and the vegetational bands have all sort of expanded northwards. They've all sort of encroached into the current day Sahara. So the white is really limited to very little patches. Your grassland and wooded grassland vegetation is really expanded into the Sahara. And that's accompanied by a lot of drainage cropping up in the Sahara. So like a lot of mega lakes, for example, this one is the mega lake Chad. But also you see, we know that there were a lot more oases, there were a lot more drainage channels. In fact, over the Western Sahara, there is this huge paleo drainage channel called the Taman Rasset, which has been detected on the basis of satellite imagery, and it far exceeds whatever we see about the Nile today. So essentially just a much, much wetter Northern Africa and very little desert. And just to keep in mind that the Sahara itself is, well, it's almost the size of Canada. It's almost 3 times the size of India. I'm sorry, I don't have a comparison with South America, but just to say that it's a really, really huge land area. So when something this drastic happens, we do expect that it would have repercussions on the global climate. Okay, so keeping this in mind, we wanted to sort of, the original intention of my PhD was just to start looking at the Green Sahara and what happened there, and generally looking at Northern Africa. And I will link this to South America, but one key challenge for simulating the mid-Holocene adequately is that most climate models do not simulate an adequate increase in precipitation. So when you start looking at the mid-Holocene, you see some increase in precipitation over Northern Africa, but it's just not enough to sort of match what the proxies say. And it's just not green enough to really talk about a Green Sahara. So keeping this in mind, we designed this study, which, I've got 4 climate models here in this, in my study. It's EC Earth, the isotope-enabled community Earth system model. This is the NCAR model. EC Earth is the European Consortium model. Then there is a University of Toronto version of CCSM4, where they made some changes to the ocean to make it more paleoclimatically suitable. And then last we've got the IS version E2.1G, just in case. So these are 4 different and pretty independent models. And all 4 of them were like these simulations were carried out independently. So I should point out that this is not an exactly coordinated study, but it comes near enough. And for each model, I looked at 3 different simulations. So a standard pre-industrial, a standard mid-Holocene, which I'm going to be calling MHP-MIP, and then a mid-Holocene with a Green Sahara, which I'm going to be calling MHGS. And just to explain what I mean by MHP-MIP here, so I'm referring to the Paleoclimate Modeling Intercomparison Project, and it's a huge project which involves coordinated experiments between different modeling centers or different modeling groups. So essentially, everybody just agrees to run these specific experiments in in very specific ways, just so that you can have intermodel comparisons like this. Yeah, and PMIP specifies forcings and boundary conditions for these different experiments that they want to include. So for example, this is how they've specified the forcings and boundary conditions for PI control, our pre-industrial control simulation, then the standard mid-Holocene, which I'm referring to as the MHP-MIP, and then this is for the past interglacial. But the key changes with the mid-Holocene simulation are the changes to the orbital parameters and the greenhouse gases. But everything else, so the solar constant, paleogeography, ash sheets, vegetation, aerosols, all of these can be kept the same as the pre-industrial. And this is a bit of a leap. So in case you have, well, if you're working with a model which has dynamic vegetation, you would definitely have better luck because you could just have interactive vegetation. It should take care of some of the things related to the Green Sahara. But if you don't have interactive vegetation just yet, this is really a bit of a leap to say to prescribe the same vegetation for pre-industrial and for the mid-Holocene, especially over Northern Africa and Arabia and those regions. So keeping this in mind, this is why we have the standard MHP-MIP simulation, which just has changes to the orbital parameters and the greenhouse gas concentrations. And then in addition to that, the MHGS simulation also has different changes. So this includes vegetation changes or dust or soil or lake changes. And as I pointed out, it's not exactly a coordinated study. So different modeling groups used slightly different ways to simulate the Green Sahara. So for example, when I say reduce dust, in the ECR simulation, there's an 80% reduction in the dust, which also then leads to a negative reduction in the aerosol optical depth. 80% reduction compared to the pre-industrial, I should add. There are vegetation changes in all the models that I'm showing. That's standard, but just to give you an idea, like in CESM, there is this increase in % vegetation cover over Northern Africa and Arabia, and something very similar in the University of Toronto version of CCSM4 as well. But in addition, this simulation also included the presence of several lakes over Africa, and the major ones, for example, Mega Lake Chad and the Fezzan. These were lakes large enough to really impact the local climate. So they included that in the simulation as well. Okay, so moving on. I want to show you the changes and mean annual precipitation first. And something that we expected for the image. Okay, here I'm showing the mid-Holocene PMIP anomalies with respect to the pre-industrial. This is again just the orbital forcing and the greenhouse gas concentrations. And we already expected to see a bit of, do you see my cursor? Okay, you do. We did already expect to see like the increase in precipitation over Northern Africa. That's explained simply by the changes to the orbital forcings. Because during the mid-Holocene, the perihelion, which today it occurs in boreal winter, it was shifted to boreal fall. So this essentially enhanced the seasonality during the mid-Holocene for the Northern Hemisphere. And there was decreased seasonality for the Southern Hemisphere. All over the Northern Hemisphere, all of the monsoon regions did experience an increase in precipitation simply due to these orbital changes. The greenhouse gas concentration changes were not, there were some changes, but I don't think they're the most important piece in the puzzle. So this is where it begins. It begins with the orbital changes. And so just simply based on the reduction in austral summer insolation, we would also expect a slight drying over South America, especially regions of the South American monsoon. So this is what we kind of expected. This is very similar to what the PMIP4 multi-model ensemble says. This is it aligns also with the PMIP3, like the previous versions of the different PMIP multi-model ensemble results. So, and then of course, as we expected, there's this intensification of the southwesterly winds, which is bringing all this precipitation, all this moisture from the Atlantic into the Northern Africa. A bit of some suggestions of a slight northward movement of the ITCZ here. But when we add the Green Sahara into the picture, you immediately see there is this rather drastic, I would say, amplification of all the same signals. So there is a considerable increase in the precipitation over Northern Africa, and a similar, like a comparable amplification of the drying signal over South America as well. So this is where this is where I'm trying to start linking this, even if you're sitting in South America and if you're studying the Holocene, because the Green Sahara period covered a lot of the Holocene, it's really important to compare or to look at modeling studies which do have the Green Sahara in, like they have either in the way of prescribed vegetation changes or at least with interactive vegetation. And that's a slight limitation of the PMIP4 multi-model ensemble, which turns out to be usually a very popular choice to, especially for proxy people. If you want to carry out a comparison with models, usually the popular choice would be to look at the PMIP4 multi-model ensemble. And it makes sense on several different levels. Of course, you want a multi-model comparison, but most of those models do not have any vegetation changes over the Sahara. And I would argue that it's sort of like it's a cause and effect thing. And in the cause part of the teleconnection, if you're really underestimating whatever happened in Northern Africa, you won't be seeing drastic changes in South America like we do. Okay, so just because the West African monsoon and the South American monsoon operate in different seasons, and also because there were changes to the seasonality over the calendar year, we also looked at month-wise but multi-model means of the precipitation changes. So we already did know previously that the South American monsoon was weakened during the mid-Holocene, but primarily this was discussed in terms of austral summer only. When you put in the Green Sahara in the picture, you see that, first of all, the most drastic changes that happen over Northern Africa are, of course, not during austral summer, but austral winter. And that also really pulls up the ITCZ and pulls up the moisture band away from South America. So there is considerable drying in Northern South America during boreal summer. And then really during hang on, I keep getting confused between the austral and boreal thing, but during boreal fall, we start seeing a lot of drying, which does not come up when you look only at the orbital insolation effects. So my idea here is that it isn't a drying related just to the weakening of the South American monsoon. It is really much more year-round, which also makes sense because the amplification of the West African monsoon happened for a longer time period and was not restricted just to boreal summer. So really there is much more extensive drying over South America in terms of both like spatially and temporally through the calendar year. Let me see. Okay. So, okay, we have this new set of simulations, and I'm arguing that this is a better set of simulations, especially if you want to start seeing teleconnections. But what's really the evidence for that? So here I've plotted a lot of different proxies over Northern Africa and over South America. Over Northern Africa, this is largely the pollen and the lake level data sets. Over South America, this is a multi-proxy synthesis by Gorenstein et al. This is a relatively recent compilation. I think it came out in 2022. So we feel quite confident that it captures most of the proxies that have been, most of the records that have been constructed over South America. And what we did is we calculated the weighted coherence kappa score. So the way it goes is that I look at the model output and I look at what the proxy signature is, and I give this agreement a score of 1 if they both say it's drier or it's wetter at that location, and then 0 for complete disagreement. And then sometimes you have this no signal in one of the two. Perhaps the proxy says there was no real great change at that site during the mid-Holocene, so we call that a near miss, and we penalize the coherence kappa score adequately. So this is really just a quantitative, well, it's a semi-quantitative measure of proxy model agreement. I say semi-quantitative because the first step, the actual agreement, that's just qualitative. It's agreement, either it's disagreement, or it's a near miss. But then after that, you can put together all of these different proxies. And I think there were close to 200 records that we considered. So this is a reasonably good number. And then we weight it and we calculate the kappa score. And for all the 4 models, we see that the MHGS simulations agree far better than the MHBMF simulations, which sort of like, it's reassuring because I want to be able to say that my new simulations are better and we've come up with something nicer and more helpful. This increase in the coherence kappa score is valid for the whole study region, or only North Africa, or only South America. It's a near universal improvement in proxy and model agreement. So that's part of the validation. Okay, so I think like I'm going really fast, is it? Anyway. Next questions are about like if this is by some coincidence an effect that we see only with these 4 models or with these 4 ways of simulating the Green Sahara. And I would, of course, like very much to add more simulations, more types of simulations, in the sense that so far I've only looked at the equilibrium simulations. But I would also really like to see transient simulations and really compare them with the longer Holocene-wide proxy reconstructions. And then, of course, with whatever new proxy data comes up, I would like to reevaluate this, say, a couple of years later, just to see if we are still on track. In terms of more model validation, we have started looking at a 5th model, HCM3. This is also a center which has done some work with the Green Sahara. And so far it looks good. It amplifies the drawing which the orbital forcing was already showing. And the Green Sahara does sort of show consistent changes both over Northern Africa and over South America. Apart from this, I'm looking at a few different mechanisms, trying to figure out what exactly it was that the mechanism behind the teleconnection, I would say. So we definitely see a northward migration of the ITCZ, although it's one of the previous studies have talked about an expansion and not a migration of the ITCZ. Our study indicates more of a migration. An expansion of the ITCZ would not lead to as much drying as we see in our results. Then there are discussions of a weakening of the upper level Bolivian high, which then subsequently led to the weakening of the South American monsoon. We do see it, but it's only part of the picture, because definitely there needs to be something which explains the drawing in the other seasons as well. I'm trying to link the changes in the equatorial Atlantic and the equatorial Pacific. So one of the other studies that I'm currently involved in, it looks at the effect of the Green Sahara onto ENSO, and then how that fed back into South America. That would be a really interesting thing to tease out, which of it was the Atlantic pathway and which of it was the Pacific pathway, which sort of feels like a U-turn, but I'm beginning to believe a lot of different teleconnections associated with the Green Sahara. And lastly, whatever changes that happened during, say, the austral summer austral winter would also likely have carried on to austral summer because of, say, like soil moisture feedbacks or a lot of different land surface feedbacks, which definitely account for the amplification of the West African monsoon. So it would be interesting to see how much of a role they play in the drying over the of South America. And at a later stage, I would very much like to see if this also, how much this plays out during the past African humid periods. For example, the African humid period during the Eemian was a lot more intense in terms of just the greenness of the Sahara. And would it have led to like greater drying of South America, or perhaps like how this is modulated by the changes in orbital forcing specific to the last interglacial? So these are some of the things which would be very interesting to, I would be interested in looking further, or if somebody has any ideas, then I would be interested in discussing this further, definitely. And just to put these things into a broader picture, here I've just sort of compiled the studies that I know of regarding the remote impacts of the Green Sahara. And there's everything right from Arctic climate to tropical cyclones to ENSO variability. We broadly focused on the climate of South America, which, yes, I should mention, actually, there was also a 2009 study, which I missed adding here, but there are only these 3 studies that I know of which have ever looked into vegetation changes and their effect on the hydroclimate of South America. And of course, a host of studies which show how the northern hemisphere monsoons are intensified due to the orbital changes, but a lot less going on in the southern hemisphere, definitely. So my point just being that if you're studying the Holocene, you can't afford to not include the Sahara in your analysis. It's just, I don't know why we're still doing it. I think part of the reason is because vegetation changes are not, they're not as straightforward to model. And just the different ways of modeling the vegetation changes ends up lending so much uncertainty to the analysis that most people just try to sort of skip it altogether. But I want to show through my work that it's not really a good option to go for, because most of the effects of the Green Sahara that I've seen are comparable in terms of their impact, say in terms of precipitation or temperature changes, or even like variability changes. They're comparable to the effects of the orbital forcing. So if you wouldn't leave out the orbital forcing changes, then why would you leave out the Green Sahara? So yeah, it tends to just amplify the effect of the orbital forcing, but it's really comparable in magnitude to the changes. I think I've covered everything I wanted to say, but this is too brief. I've got more stuff that we can discuss. And this is where I wrote down my results. So, just in case, please take a look and let me know if something could have been done better. I would appreciate that.
Many thanks, Shivanshi. Your presentation was wonderful, and yeah, it blew my mind. A lot of things, thinking while you were presenting us. So, do we have any question in the chat, or someone that want to raise a hand and go ahead? Rodrigo, as always, very active.
Always, I know. It's because we have a lot of questions always.
No, we
Thank you
love
so
to
much,
have you.
Always. I love to be here too, Karina. So thank you so much for the presentation. It's really interesting, and always these models are really helpful to the paleoclimate people like me. For example, we don't understand how they work, but we like it. So yeah, I have a lot of questions, but I think I'm gonna reach you by email later. But I would like to know how complicated it is to run the models that you present today, because you have 5 different models, no? And I suppose that all of them have different issues, no, that you must know how to manage, no? Like what kind of data you are input on the models, which are the resolutions and these kind of things. And then I can make another comment, but first this question.
the models that I listed here, none of these simulations have been run by me, just to point out. I ran my own simulations for an atmosphere-only model, and these are all coupled ocean atmosphere, coupled ocean and atmosphere, but not dynamic vegetation, just to point out. So I think the more coupling you do, it tends to get more and more complicated. I've run my simulations only with atmosphere-only model. An atmosphere-only model, which is called the GEM model. It's a Canadian model that we use at UQAM and some of the other centers in Canada. To say how complicated it is that, okay, so we have a good grip on what so a model needs some inputs, right? Inputs in terms of how different the climate was during the mid-Holocene compared to the PI. We start off with a pre-industrial simulation, or say a present day simulation, and we run a simulation for the present day. We just compare how well it's doing relative to the observations, and then we run it for the past. All I'm going to say is it can be painful. It's just one of those things which, if it works, it's very easy. The model is supposed to do its calculations all by itself. It doesn't really like to do it. It likes to make people, dance a bit. So it can be very, it can get more streamlined as the modeler gets more experience. I'm sure it's like I'm also part of the problem. But some of these simulations are like 1,000. Let me just give you an idea. Hang on. So 100 days, 100-year simulation, for example, can take maybe a week to run if all goes well, which again may not go well. I can't really speak about how long it took those people to run their simulations, but there were a lot. So I would expect like at least a month of just running the simulations or troubleshooting or debugging. That's it. Was this the question that you asked? What do you meant?
Yeah, no, the thing is, I'm curious because right now I'm doing a review of precipitation proxies for the last glacial maximum, so it's not the same time, but not in South America, but in Central America and Mexico. No, so like the neotropical area in the north. So I was wondering if like that it was possible, because so far I have only the proxies, the runoff proxies.
Right.
In all this region that are like, I don't know, like 80, something like that points. But I was wondering if it's possible. I know that there are models for the last glacial maximum that I can compare with, but as I understood to a colleague who works also with models, the resolution is not like enough to cover only this specific area, no? Like the models are like globally, but not. Yeah.
The models that I included here have like the highest resolution is 1 degree by 1 degree. So that's around 100 kilometers in the equator, I think. And the worst resolution was actually the 5th model, which I didn't add, but it was 2.5 by 2.5. So these are coarse simulations. Of course, you can run very fine simulations. It just depends on the resources that you have. But if you wanted to compare something with the PMIP4 ensemble, for example, I can't speak to how well. I'm saying this because I say if you were to look at the Holocene, maybe looking at the PMIP4 ensemble is not adequate. I don't know if I should make the same statement about LGM. I have not worked with the LGM, but there are model outputs already like freely accessible for the LGM, and it's a popular PMIP experiment. So I'm sure there are a lot of modeling groups which participated in it. So that's easily like publicly accessible.
Okay, good to know it. And just quickly before Christian, because I get he has a question. In these factors that you were saying at the end, that you need to consider like the migration of the tropical convergence zone and these kind of things. I will suggest like the altitude or the orography of the continent, because in this review of the last glacial maximum, what I am observing is that all the high altitude records, for example, in central Mexico or in Colombia, where is this Lake Bukene, I think, all these sites, the response on the precipitation doesn't depend on or seems not to depend on the atmospheric area, the atmospheric forcings, but the altitude is like, influencing on the distribution of the
Yes.
rainfall, I think. So that was just like a comment.
I can confirm that the orography in these models that I showed, it's not great. It starts breaking down when we go into the high altitude regions. So I don't think I have anything specific for it, but I mean, I just mean like the whole Andes chain. It's not adequate by at least like, I think the orography misses it by at least like 800 meters or close to a kilometer in some regions, and it's just one of the limitations. I get that because it's a limitation of what you can put into the model and how fine you can go. So I have not tried to go into the high altitude regions at all for this reason. So yes, I agree.
Well, thank you so much.
Christian, go ahead. Your turn.
Thank you. It was I really liked the presentation. I was a little bit lost in some parts because this is not my field, but I could understand some of the things. And I actually, during your presentation, I saw the maps, and I really liked that how you presented this kind of teleconnection. And then I remember, because then in the past I worked before in the Andes, and then I had some reconstruction. And then there's one of the, I think, bibliography that they talk about this weakening and strengthening of the intertropical convergence zone, especially in the late Holocene, for the Little Ice Age, for example. Then I was curious to see if you have kind of tried to correlate with other events where this intertropical convergence zone has also weakened or strengthened. That's one of the questions. And the last question, second question, quickly, is it how confident are you with the modeling for hydroclimate? Because I always hear that is one of the most difficult parameters to even to reconstruct. So I guess for modeling is also even more difficult. So those are my two questions.
So I'm gonna answer the second one first. Any of the white patches you see here are places where I've statistically cleaned out the very small values, which could be attributed to just like differences in the distribution of the pre-industrial and the mid-Holocene precipitation. So anything that remains here, I'm very confident about it. Also because first we understand the physics behind it, why it happens. And then because all the models are showing pretty comparable values. So for example, I agree that like EC Earth has much higher precipitation amounts compared to GIS, for example. And I do understand a bit of it because EC Earth, the simulation was run with a previous like PMIP3 protocol, which all PMIP3 models ended up showing warmer and wetter climates. Okay, but if you keep away EC Earth or at least the wettest parts of the EC Earth results, I think because everybody's roughly showing about a 2 millimeter increase over North Africa, and then like up around a 1 in some places, a 2 millimeter decrease per day over South America, and of course like different regions, I see a pretty good coherence. So that's why I feel pretty confident about it. This is not to say that models, well, of course, there's parameterizations which go into the precipitation calculations, but it's decent also because I compared all of these models, their pre-industrial simulations with present-day observations. And every model has some biases, but it's roughly consistent. So if you want to zoom into specific proxy sites, I would not go by, I wouldn't go by specific amounts, but you can definitely talk about like qualitative, like increase in precipitation of say like of this magnitude. I'm confident about it. The other question was about the Little Ice Age or about any other period which might have seen like changes to the ITCC. Well, I'm limited in this to answer this because my I don't know if I wrote it somewhere, but maybe I should. Well, yes, all this mid-Holocene simulations are just for the period 6Ka. So even if they are 200 or 1000 year simulations, in some cases, it's not 6000 years ago going to 5000 years ago. It's just 1000 years running the same calendar year, if that makes any sense. Like all of these are only equilibrium simulations, and I have not yet looked at transient simulations. So that sort of like constrains me. I can't really look at anything else apart from the mid-Holocene with these outputs. But I'm not, I mean, I off the top of my head, I can't right now come up with a study which has already done this. So perhaps like I would have liked to answer your question, but I don't have the answer.
Thank you very much.
Great. Givenchy, I have one last question, I think. I wonder how hard was for you. And I think that you need data from paleo reconstruction from South America. So I wonder how hard was for you, if you find that the available information was enough, or if you think that there is some areas where more information about paleoclimate will be needed. And second, I wonder how do you see that this can help us to understand future global changes related with the climate, right?
So about the proxy distribution, let me see if this helps.
I was surprised with your map showing all those points. That is a lot.
Yeah, I mean, it's decent. It's good enough, except like it's patchy. So I would like to see a lot more in the northern regions. I would like to see a lot more. I mean, that's just how it is, I suppose, and I can't really say why. But this is multi-proxy, so I'm sure people have tried their best to go to different regions and come up with different enough results or reconstructions. I can't complain, but of course, as a modeler or any person, you would like to see a lot more points if possible. The one thing I would say is that there is a lot more disagreement going on over the southeastern coast itself. Disagreement between the proxies, I mean. So like in the same region, the model is showing a drying all throughout. But in some places, the proxies do not agree with that, and in most places, they do agree with that. So this is what I mean. So perhaps it would be nice if well, I don't know whose job it is, the modeler's job or the proxy person's job, or perhaps a compiler's job, perhaps. But just to sort of smoothen out these interproxy disagreements before we can compare them with the models. That's the part that only a modeler should not try to do. I feel like they would not know enough to smoothen out the interproxy differences. The other parts is one of the questions that came up in review for this paper was what happened in northeastern Brazil, and it seems that there was quite some disagreement over there. So perhaps that's an interesting part to look at, but. Yeah, I wouldn't. Hang on. I would very much like to look more in the Amazon. From my results, like I don't think the Amazon could have dried out. It's not in the sense that it didn't reach any tipping point in terms of vegetation. It continued as a rainforest, probably suffered a bit, but still continued as a rainforest. But still a lot more could be done here just because there are different things happening in the different models, but also within the same model. So that's Amazon and Northeast Brazil for me. And maybe fill in this patch right here.
Yeah.
That's from the proxy side. How this could help. Okay. Most of my work just says the same thing over and over again. First, that land surface feedbacks, which including vegetation feedbacks, are really very important. So we did it in a very crude way. We just prescribe the vegetation changes or the associated soil or lake changes, but ideally, if you want to look at the future climate, you should be having, like, you should be including dynamic vegetation or like interactive land surface modules. That's the first key thing, that these land surface changes can really throw in surprises and can really amplify any of the original forcings. That's the first key point. I suppose the other is that that's more Holocene specific or Green Sahara specific, but it's more like these kind of teleconnections can sort of throw in surprises in our analysis. So if they're not adequately represented, and the way to adequately represent a teleconnection is to first adequately represent the source of the teleconnection or the source of the effect. So if, that brings us back to the land surface changes in this case. This is what you could take out from my like paleoclimate work and also apply to the future.
Great. Many thanks. Rodrigo.
Yeah, just a quick question. When you say vegetation, for the in the models and stuff, you are referring like because the coverage of the vegetation can influence on the albedo, and
Yes.
then that affects the precipitation?
Yes.
Because I am thinking, like, well, if you are talking about taxa of pollen, for example, well, different taxa not only depends on the precipitation, but also in the temperature, for example,
Yes.
or the geology also can influence on the presence of certain taxa or not, but so
The
yeah.
first major change that we saw in all the models is this huge change in the albedo, and that's quite a lot. So the desert surfaces are something over 0.3 usually. Like this depends on different studies, but I think 0.3 is a fairly representative value for albedo over the over a desert region, and it drastically reduced in all our models. This depends on how you prescribe the vegetation. So for example, if my model has only a few different categories, or like what they also call the plant functional types, and then how those translate to the vegetation over this to the albedo over the surface. So this value, it depends on how your model looks at the vegetation, of course. But that's a very drastic change, and that's the first order change that happened really over the whole Sahara. So there was this huge thermal heat low, which also then intensified the whole circulation over northern Africa, sort of pulled moisture away from other regions that might have received it from the tropical Atlantic. And then a host of other oceanic changes in the tropical Atlantic, changes to the Walker circulation, which then also translated it to the changes in ENSO variability. So it's the first order changes. It all begins with the albedo changes.
Great. Any other question? Seems that not. So we thank you, Sivanji, and we congratulate you for your work and this amazing presentation. Many thanks. And
Thank you for having me.
You're welcome. Anytime. So our next meeting is October 4. So you are all welcome to join us to hear a talk about making sense of the paleoscience in Latin America, co-production and relativism. Our guest lecturer is Carlos Avedaño. So we wait for you to join us in our next meeting. So thanks everybody, and see you next time.
Thank you so much. See you.
Bye-bye.